All right, so we're going to start off with the types of labs that you are required to know based on the syllabus. So these are the topics that CXC wants you to cover. Separating techniques, acid-base salts, redox reaction and electrolysis, qualitative analysis, volumetric analysis, rates of reaction, energetics, and saturated and unsaturated hydrocarbons. All right, so question, everyone know at least half of this list? Are we aware?
Yeah.
Anybody else?
Hi, good afternoon. Yes, half.
Just half. All right, so let's identify the difficult ones that you are not aware of, and we cover those. Then we'll look at the questions that will cover the basic ones as well. All right,
Okay.
so what are the difficult ones, are the ones that you're not aware of? Well, based on silence, I think everybody knows them. 3, redox reaction and electrolysis.
Yeah. Yeah.
Any other?
5.
5. All right, so those are the 2. Anyone else has any problem with or not clear on any of these? All right, so no one else. So those 2 we will look at now, and then we go to some questions. All right, so redox reaction and electrolysis. So the important part here is the electrolysis setup. So how do we actually carry out an experiment about electrolysis? All right, so in electrolysis, what we create is actually known as an electrolytic cell. And what that is, it's just a complete path for which current can actually flow through a substance. So we have a container that has your substance, right? And then in that substance, there are 2 rods that are immersed in that substance, and those 2 rods are connected to an external battery supply, right? So this exactly is what the electrolysis setup entails. All right, so the thing now is to know what does each of these represent. So let's go and label each set. All right, so the rods that are immersed in the substance, these rods are known as electrodes. So this one here and this one here, they are collectively called electrodes. So these are electrodes, right? And they are 2 different types. So they are charged with a positive and one is a negative. Now, to know which side is a positive side and which side is the negative, then we look at the battery connection. All right, so from the battery connection, we see that this is the positive side of the battery, this is the negative side. And how we know that is because the longer strip, so the longer line here represents the positive, the shorter line represents the negative. So the positive side of your battery always connects to the positive electrode. Your negative side of the battery always connects to the negative electrode. All right, so now we need to know they 2 have different names. So the positive one is called an anode, and the negative one is called a cathode. All right, and one last thing that needs to be labeled would be the liquid that is present inside the container. Anyone knows that the name of that liquid?
The electrolyte.
The electrolyte. So the electrolyte is the substance that completes your cell. Now, the electrolyte can be either in the form of molten or a solution form. And by molten, what do you think I mean when it's molten? Anyone? What do you think molten means?
Melted.
Melted. So molten in this case means it's melted, and solution would mean that it is mixed with H2O, right? So let's look at how this actually works. So electrolysis is primarily used. So the definition of electrolysis is the use of current to split ionic compounds. And that's important because electrolysis only works with ionic compounds. And that's because ionic compounds are created by using cations and anions, right? So when we split a ionic compound, it actually will create the separate cation and the separate anion from the compound itself. So if we take, for example, sodium chloride solution, right? So we have sodium chloride solution. If we pass electricity through this, it breaks up sodium chloride into its two ion form, which are Na plus and Cl minus. Now, when the compound actually splits into its ionic form, then the purpose of your electrodes would be to actually either distribute electrons to it or accept electron from it. Now, since we have the ions, the cations and the anions, then the electrodes, how do you know which one goes to cation, which one goes to the cathode, and which one goes to the anode? So let's use sodium chloride, for example. Where would the Na plus be attracted to?
The negative electrode.
So the Na would go to the negative electrode, and therefore the Cl would actually go to the positive electrode. All right. So when that happens, then the preferred ion would be discharged, and discharge means that if it goes to the cathode, it's going to, so the sodium will go to the cathode, and that means that if it's being discharged, it will actually gain electrons to become a sodium metal. So we're getting sodium metal from sodium chloride, right? And if the chlorine is discharged at the anode, then that means your chlorine will actually lose the electrons and it becomes chlorine gas, right? So basically the electrolysis is passing the current through ionic compounds to split it to get different elements or gases at the end, right? So we either produce different elements or we produce the gases that created the ionic compound. Now, electrolysis entails a lot more technicalities to it, which we'll look at a question to fully understand it, right? But this is how the experiment is carried out, right? So we have a container that has your solution. Either you heat the solution, or you mix it with water to create a solution. You have two rods. One is a positive one is a negative one that's connected to a battery supply that will supply the flow of current. All right, so is that clear for electrolysis for everyone? All right, next one is the volumetric analysis. Now with volumetric analysis, this is the term that you probably aware of that says it's titration, right? And everyone is aware of that term, right?
Yeah.
All right, so let's see how we set up a titration experiment. So in titration, we have a stand, right? And on the stand, we have this lovely thing here, and it has a top, right? And then we use something else that looks just like this, and we have something else that looks just like this, and we have a beaker, right? So let's go. So we know the stand already, that is right there. Now, what is actually clamped to the stand? Anyone knows the name of this device that's clamped on? What's that?
No.
No one?
Nope.
It's a burette.
It's a burette.
Oh.
All right, so that instrument there is a burette, and this one here is known as a pipette.
So,
This, yes,
where's the difference between a burette and a pipette?
yes, I'll soon explain the purpose of each. But good question. All right, next one is a conical flask, and then everyone should know a beaker.
Yeah.
All right, so burette. Now, the purpose of a burette is to actually, one, it holds the liquid that you turn the tap at the bottom here. So this little gap here, this tap, if you turn it slightly, there is a hole in it that if you turn, it allows the liquid to flow through. If you turn it again, it allows the liquid to stop. Right? Now, on the burette, we have scales, which are the markings on it to give you the volume of the solution or the compound that's present in your burette. Now, your burette can hold a maximum of 50 cm cube, right, of a solution. Now, your pipette, it cannot alter the flow of the liquid. So once you start allowing it to flow, it just continues to flow. Also, it can only hold a maximum of 25 cm cube of a solution of a liquid. So this holds 25 cm cube. Burette can hold a maximum of 50 cm cube. So what we normally use is we use a pipette to actually always use 25 cm cube of a solution in the pipette, and we release this pipette into the conical flask, right? Now, once that liquid is in the conical flask, we add what is known as a indicator. And everyone is aware of that term, right?
Yeah.
All right,
Yeah.
great. So we use an indicator. So we use drops of indicator, normally 2 or 3 drops of the indicator in your conical flask with the solution. And then we actually put this flask under the mouth of your burette. Then we turn the tap to get drop by drop, right? So after each drop, we will actually shake the conical flask to actually see at the point in which there is a color change. Because we use the titration that we focus on at CSEC level is the acid-base reaction. And we know that acid-base reaction says that once the acid mixes with the base, right? Once it's completed, it's going to form a neutral solution of a salt. And that neutral solution will have a different color at that point. So that's the color that we look for based on the indicator that we use, right? So once you notice a color change, then we stop allowing the substance from the burette to drop in the conical flask, and we measure, and then we read off the volume that is required from your burette to actually cause the the solution to change color. And so that's exactly what the titration or volumetric analysis entails. Right? Any questions about that? No questions?
No.
All right. All right, so that's basically what the titration or volumetric analysis is. And once you carry out titration, then you're normally asked to do calculations that relate into moles and concentration and such. We're going to look at questions like that. All right, so these are the experiments that are needed to have an idea of when you're doing paper 3 of chemistry. All right, so let's see how much questions we can go ahead and look at. All right, so we're starting off with June 2012. All right, so it says an experiment was carried out to investigate the effect of temperature on the physical state of substance X. So the solid X was heated until it melted. The temperature change that occurred as the hot liquid cooled were recorded. Some of the results are shown in Table 1. The other temperature readings are displayed in Figure 1. So read each of the temperatures displayed in Figure 1 and record them in the appropriate space in Table 1. So that's a easy part to do here. So let's go. So at 4 minutes will be the temperature reading. Yes, anyone? At 4 minutes?
57.
So at 4 minutes, it's 57. So 57.0. At 6 minutes?
56.
So 56.0. At 12?
5.7.
So at 12, it is 55.7, yes. At 14?
5.3.
55.3. And finally at 16?
54.5.
54.5. All right. So those are your temperature readings. Now it says use the data in table 1 to plot a graph of temperature of substance against time on the graph provided. Some points are already plotted. All right, so we need to plot the ones that we just added to the table. So at 4 it was 57. So 57 would be halfway between 56 and 58. This is going to be a little bit hard. So let's use this. Not right there. All right, so 4. So 4 is the fourth line on your X, which is this line here. And then 57 would be halfway. There's 1, 2, 3, 4, 5, which is this line right here. So where these two lines meet, which is right here, that's where we put our X. That's the first one. The next one was 56, and 56 was at 6. All right, so this is 6. And we go up to where 56 is, which is at this line. And we put that there. All right, 8 and 10 is done, and 12, which is 2, 3, 4, 5. So this is 11. 1, 2, 3, 4, 5, and this is 12. All right, so 12 is this line here, and 12 was at 55.7. So 55, which is 1, 2, 3, 4, 5. So this is 55 here. This is 55.246. So 7 is the space under it, so it is right here. And at 14, it was 1, 2, 3, 4, 5, and 14 is right here. it was 55.3. So that's 1, 2, so this space here, which is right there. And then your final one was 54.5, and 54.5 would be in this space here, right there. All right, and then it asks to do a curve, a best fit curve. So you'd start, pass through each point. Here it is, and then we go down like that. All right, so that's how the curve will look.
Sir,
Yes,
that's called a best fit line. That's what it is.
could you repeat that, please?
It's called a best fit line.
No, this is a smooth curve. So a best fit line is just one straight line.
Oh, okay.
But this, it says draw a smooth curve. So it would just go through each point, ensure that the curve is kind of smooth. All right, it says from the graph, determine the value of the melting point of the substance. All right, let's see if I can put it back. All right, how would we find the melting point of this substance? Anyone knows? Could you repeat that?
When the temperature rises the most,
When the temperature
rise the most,
rises the
is a
most?
solid. Is a solid medium.
All right, all right, so let's, all right, so this curve here is known as a cooling curve, right? So it shows the period that when it's at a liquid stage and then it cools down to be a solid, right? So in a cooling curve, it's primarily, the full shape of a cooling curve looks like this, right? So if we start with a liquid, so that means the first curve here, that's when the substance is a liquid, right? Now this part here, when it's a straight line, is when the substance is changing from a liquid to a solid. So at this point, it's a solid. All right, so we can see a little resemblance there to the curve that we drew. Now, if it's at the point where it's changing, it's when it's flat, then that means that changing point is our melting point right here. So the point where it's flat, that is your melting point temperature. Because melting is changing from solid to a liquid, so solid to liquid, melting. All right, so on this curve, or if we look back at the table, we notice that we had constant temperature at when it was 56. All right, because we notice at 6 it's 56, at 8 it's 56, and at 10 it's 56. And that's at this point in your graph. So therefore, your answer for this would be 56. Everyone got that?
Yeah.
Right. So the melting point here would be 56 degrees Celsius. And then from your graph, determine the temperature of the hot liquid after 3 minutes of cooling. And I just canceled that off. All right, let's see if I can estimate it. 1, 2, 3. So at 3, it would be like 58 degrees Celsius. All right, but you just use your graph because I removed the curve here. So you'd find 3 minutes at the bottom here, which is your third line here. And you just go up to where it meets the curve and then come over, and that temperature would be your temperature. All right, so for this purpose, we're going to use 58 degrees Celsius. And then what is the physical state of substance X at 6 minutes after cooling? So at 6 minutes, that's when it's at the straight line here, when it's flattened out. What would be the state there?
Solid and liquid.
Solid and liquid, great. So when it's changing, it actually is both solid and liquid. All right, so compare the arrangement of the particles in substance X at 2 minutes. So that's when it's at liquid stage, and at 16 minutes, that's when it's at a solid state. So 2 minutes would be when it's on the curve, first curve here, which is liquid. 16 minutes when it's coming down, so it's a solid. So at 2 minutes, what would be, how do you compare the particles when it's 2 minutes? Anyone? Any answers? 2 minutes when it's a liquid. What's the arrangement of the particles as a liquid?
It's the connection is kind of weak, like it's medium.
So the attraction,
The attraction is is medium.
is medium. What about the spacing between them?
For liquid,
And
it's not close together. It's not got
For liquid, it will be freer than a gas. Sorry, a solid. And a solid is tight.
so it has more spacing than when it would be at 16 minutes, which is at solid,
Yeah.
right? And then we could just add one thing for the 16-minute part, which would be that the attraction, so the attraction in a solid would be what?
it will be close together. It will have a high attraction.
High or strong. So strong or high attraction, and particles are very close, all right? All right, so next part says an experiment is carried out to determine the percentage deposit of a mass of sand and copper 2 sulfate in a mixture. A 10-gram portion of the mixture is stirred in 200 centimeters of distilled water until no further change takes place. The resulting mixture is filtered into a clean beaker using a funnel fitted with a filter paper. State clearly what is observed. All right, so state clearly what is observed in the beaker and on the filter paper at the end of the experiment. All right, so the first thing to note is what exact topic of chemistry this question is portrayed to. Anyone has an idea? Anyone? Any idea of what this?
Since they're using filter paper and filter funnel, I guess separation.
Okay, so
Technique.
separating techniques. All right, so if we're using separating techniques, and specifically this one is about filtration. And we know that filtration deals with, you have a mixture where a solvent is not able to dissolve a solute, right? So in that case, then we have sand and copper 2 sulfate in a mixture. All right, so we add the water to copper 2 sulfate and sand. What will happen? So if we have the beaker, right, we have the sand and copper 2 sulfate, we add water to it, what will happen? Anyone? All right, let me help you out. So we have the liquid part, and then at the bottom of your beaker, you're going to have some particles that are not able to dissolve. So what would these particles represent? What will cause the particles to settle at the bottom and not dissolve? Which particles would that? All right, so comparing sand and copper 2 sulfate, if you mix them with water, which one you think will not dissolve?
The sand.
The sand. So therefore, at the bottom of your beaker, you'll have the sand. Right? So that means this part here, the liquid part, would be a combination of water and copper 2 sulfate, which is SO4, CuSO4. Now, what is the color of copper? Anybody knows the color of copper?
Kind of silverish. Kind of.
Silver? No. Copper is blue. So copper sulfate, yes. The copper sulfate will have a blue color. So therefore it will turn the water actually blue as well. All right, so now let's look. So now if we have this in a beaker and we filter it, then it's asking us what will be observed in the beaker. So the beaker that's under the filter funnel, so let's draw it so you know exactly. So we have the filter funnel, right? And remember under it, you're going to have your beaker to collect what's going through. So what would be collected in this beaker here?
The water and the copper sulfate.
Exactly, great. So you have the solution of copper 2 sulfate. And you can be specific because it says what you'd observe. It's a blue solution. All right, so that's what will be collected in the beaker. And in the filter paper, what would you observe? What will be observed in the filter paper? So remember the filter paper is in your filter funnel, so it collects your residue, which will be your sand. So your sand residue will remain. All right, so that will be your observations for your beaker and your filter paper. All right, so next part here is the residue from B1. So the residue, remember, is the sand, was washed and dried and weighed on a watch glass of mass 2 grams, sorry. The mass in grams was recorded on a balance. The part of the scale is shown below. And we need to determine the mass of the residue and record it in the space below. All right, so it's saying that the sand, which is our residue, was washed and then the mass recorded. So to record the mass of your sand, you have to put it in a little container. In this case, they call it a watch glass. The watch glass had its mass of 2 grams. Right? And on our scale, the reading here on our scale would be 6.3. All right, so it's marking at 6.3, but we have to subtract the mass of the glass that the sand is in. So therefore, your total mass would be 4.3 grams. Is that clear?
Yeah.
All right, and then the next part says the filtrate was evaporated to dryness and the remaining solid was transferred to a watch glass of mass 2 and weighted on the same scale, and we get that reading. So what's the mass? So it's the same thing here. So at this time it would be 7.6, and we subtract the mass of the glass container, which is 2, and we get 5.6 grams. All right, so now it says calculate the percentage mass of sand in the mixture. All right, so it says that the total mass of the mixture.
Can you hear me?
Yes, slightly. All right, so the total mass of the mixture is at 10 grams. All right, it says the portion of sand. So sand was, yes?
Can you hear me? Before you move on, how do you get it? I know it's.
Oh, the 7.6?
Yes, please.
All right, so the scale here. So this is 7, right? And 5 strokes away is 8. So that means each of these small strokes would be 0.2. So this is 7.2, 7.4, 7.6, 7.8, then 8. All right, and we notice the arrow is pointed on this one here, so 7.6. All right, so the percentage of sand in this mixture, because we know that sand has the mass of 4.3, which is at the top there. So we divide, so 4.3 divided by the mass of your mixture, which is 10, stated in the question above, times its percentage, so it's times 100. So that is 43%. All right, and same thing for the copper 2 sulfate percentage. We use the mass of copper, which is 5.6, over the total mass of the mixture, which is 10, times 100 for percentage, and we get 56%. All right, and final question for this one is, add the percentage of masses of sand and copper 2 sulfate and give a value why the difference is different from 100%. So 56 and 43 gives us 99%. So why is it not 100%?
Yeah, that of the water.
Go ahead. All right, could you repeat that? I didn't hear.
Water.
Because of?
Water.
Exactly. So it's the 1% difference is because of the water that was used to mix it. All right, so that would be the reason why it's not 100%. So you can add that the 1% is due to water being added. All right, so we're just, because a lot of the papers, number 2 is normally in a table format like this. All right, and it's very easy once you actually can remember the notes that I sent earlier. All right, let me just share so we can all see it. So once you can remember the specific notes right here, then you will be able to answer any of those table format questions. And this part is so these labs are pertaining to the one that was there. So this is known as qualitative analysis. All right, so that was number 4 on the list of labs that you need to know. So this would probably be the only thing I would advise to actually spend a lot of time trying to remember, because it's important. Right? So it shows us, one, it gives us the color that will be available or will appear if a specific solution reacts with a specific ion. Right? So we look at the metal ions, calcium, aluminum, zinc, lead. Right? If we add a small amount of this substance, what color will be experienced? If we had excess of the same substance, what color, if any, will actually change? All right, so let's just run through some of these tables. So the first one here is if we're adding sodium hydroxide to a solution that has these ions present. So if we add, so notice first one here is if we add dropwise of sodium hydroxide. So that means we're just using drip by drip of sodium hydroxide to a solution that has, let's say, calcium, right? So it will actually get the color of a precipitate to be white. So there will be a white precipitate at the bottom of your solution that has calcium in it. if we start adding more sodium hydroxide to it, it's going to actually get insoluble. Right? So the small drops will start forming small white residues at the bottom. In excess, you start getting more white residues at the bottom. Is that clear for everyone?
Yeah.
All right, and then let's look at zinc. So in zinc, if the solution contains zinc and you add small amount of sodium hydroxide, you get a small little residue of white, or the substance starts to turn white. And if you start adding a lot of sodium hydroxide, then we notice the last column there for zinc, it says it's soluble in excess and it will give a colorless solution. So instead of it having a white little residue at the bottom, it's going to actually change the entire solution to just a colorless solution, just like water, right? So it's important to know in excess and when it's in small amount. So that was with sodium hydroxide. This one is if it's, instead of sodium hydroxide, we're using ammonia solution, right? We notice the different changes, if any. And then, so those were the cations, so the metals. And then for anions is the same thing. So these are the negative charges. It tells us what you observe. And also for gases, so like carbon dioxide, right? So if we need to know if carbon dioxide is produced in a reaction, then we actually will just react the gas. So the gas that's formed, we run it through a lime water, and you get a cloudy white precipitate. So if carbon dioxide passes through lime water, you get a white precipitate. It looks like a cloud, right? So these things are very important. Right, so these are the things that you need to know. These are the gases and how you test if a specific gas is present. So if hydrogen is present, then if you place a lighted splint near the test tube with hydrogen, you're going to get a popping sound, right? And the flame will actually be extinguished. If it's oxygen present, if you put a glowing splint there, so that means you light the splint and you actually blow it out and put it close to the gas, it's going to actually relight that specific splint. All right, and then for ammonia, if ammonia is present, we can just use litmus paper. So it will change red litmus paper to blue. So that's an easy one to remember. If you have ammonia gas and you want to check, it's the only common gas that is in the lab that actually is alkaline. So it will change red litmus paper to blue. All right, so let's look at this table from this question and see if we can actually answer these questions. All right, so you can bring it up on your side so we don't have to go between these two slides. All right, so first thing, we have a small amount of solid R is stirred with water. The mixture is filtered and the filtrate is separated into 3 portions. So to one portion of the filtrate, aqueous sodium hydroxide is added dropwise and then in excess. So they gave us the inferences. The inferences tells us the possibility of the ions that will be present based on your observations, right? So in this case, we're going to write our observations, and we have 2 dots there. So that means we need to show when it's in a dropwise motion, what observation would be observed, and when it's in excess, what observation would be observed. So now we have to look, since it's sodium hydroxide, we look at the table that has sodium hydroxide, and we look at the observations for zinc, aluminum, and lead. When it's in dropwise motion, dropwise, what observation? Could you repeat that?
why precipitate soluble in excess?
So when it's in smaller portion, it's going to give us a white precipitate for all these ions. And in excess, we get
Soluble.
so it's soluble. So that means it becomes a colorless solution. All right, so we will not use soluble in observation alone. So if you're going to say it's soluble, you have to say that there is no precipitate form, right? Because soluble is not an observation. Soluble is actually a conclusion. So observation would tell us exactly what you're seeing, right? And you see that the substance will actually be a colorless solution, right? Or you can say colorless with no precipitate. All right, so is that clear for everyone?
Yeah.
Yeah.
All right, so let's do test 2. So to another portion of the filtrate, aqueous ammonium hydroxide is added dropwise and then in excess. So the observation will be that it's either aluminum that's present or lead that's present. So when it's dropwise, what observation would ammonium hydroxide have?
White precipitate and it's soluble to these.
What's that?
White precipitate.
So in dropwise, it would be
White precipitate.
a white precipitate.
White.
And in excess, it would be
Insoluble.
insoluble.
Oh no, not insoluble. Wait. The precipitate.
So it's all right. So insoluble, but again we can't write insoluble. So we say we have. You could say more white precipitate. So more white precipitate. All right. All right. So I'm giving you 5 minutes to look through for tests 3, 4, 5, and 6, and you can jot it down, and then you're going to tell me what observations you would observe. So 3, 4, 5, and 6. All right. So are we finished? That a yes? Finished?
Yeah.
All right, so let's go. So third one. So third portion of the filtrate, aqueous potassium iodide is added dropwise, and lead is not present. So lead is absent. So what observation would we have if lead is absent? Anyone found that one?
No, I didn't.
All right, so important thing to note is that this compound, which is lead iodide, because once potassium iodide is mixed with lead, it's going to produce lead iodide. Lead iodide is the only iodide that is insoluble. And it produces a green precipitate. So if it's not present, then that means, what would we observe?
Colorless.
Exactly. So it's the only one that's insoluble. So every other metals will have a colorless solution being formed. because it's going to be dissolved in. All right, so next, test 4. So to the residue, dilute nitric acid is added. Any gas given off is tested with filter paper dipped in acidified potassium dichromate 6, and the resulting solution is tested further. So we have two options. So sulfur dioxide gas was given off, and the sulfite salt is present. So if sulfur dioxide gas is given off, what observation would we get for that? All right, so I'll help you out. It's under the testing of anions. It's the second table there, where SO3 2- is. It tells us that sulfur dioxide evolved on heating which turns acidified potassium manganate 7 solution from purple to colorless. All right, but this was potassium dichromate. All right, which is dichromate color is orange. So permanganate is purple, dichromate is orange. So it changes orange to colorless.
Green.
So it will change the potassium dichromate from orange to a colorless solution. So that's if the gas is produced. And then its second part says a sulfite salt is present. So what will happen if a sulfite salt is present? And sulfite is SO3. So if there's a SO3 present, then the same thing will happen where the orange color will change to colorless. So remember, so again, because this one it's not on the table provided, right? So once it's dichromate, its original color is orange. And if it says it's permanganate or manganate, then its original color is purple. All right, so test 5. So one portion of the solution from 4 is treated with aqueous sodium hydroxide dropwise and then in excess. And it says that calcium ions are produced or present. So in a small amount of sodium hydroxide, we go up now back to the first table, and calcium in excess. In small portion, we have a white precipitate. And then in excess, the calcium is insoluble in excess, so we get more white precipitate. And then the final one is the one from 4 is treated with ammonium hydroxide dropwise and then in excess, and it says calcium is produced. So we look to the next table, which is the one below that, and calcium, no precipitate, no effect. So that means it creates no precipitate. So it remains colorless. All right, that's understood?
Yeah.
Okay. All right, so that's question 2. And then let's look at question 3. It says plan, design an experiment which could be used to determine whether water-soluble black ink made by two different manufacturers consists of the same components. All right, so with the question 3, now this is where your knowledge of the different experiments that I listed there before comes in. All right, so we first have to identify which one of the experiments topics this problem is based on. So we want to know if two different black inks have the same components. So which experiment would that fall under?
This is
So would that
separation.
be paper chromatography?
Great. So separating technique, and specifically this separating technique would be paper chromatography. All right, so
So is that to test reduce the cross?
could you repeat that?
Is that the test reduce the cross?
All right, so you're breaking up, so I'm not hearing fully. Go again.
Or is that the test reduce the cross?
Still not hearing. All right, so could you just type it? You're still not hearing what you're saying. All right, so while he's typing that, all right, so we have to know the knowledge of paper chromatography. All right, so here he's saying the cross. Cross, well, different persons will use, because most times they use like a drop in, like use a little drop on the paper, or you can use a cross. Yeah, so it doesn't matter if it's a cross you use or it's just a drop of the ink on the paper. All right, so the knowledge of paper chromatography is very important in order to answer this question. But before we can do that, we need to write an hypothesis, which would be a statement based on your problem. What do you think? All right, so any good hypothesis?
We can't hear nothing from the call.
Yes, any good hypothesis? No one? All right, let me start you off with my hypothesis. That means you'd have to give me everything else. All right, so this hypothesis, let's go with an easy one that says that all water soluble black ink all water soluble black inks have the same components. All right, so that is what we think, and it's linked to the problem that it doesn't matter what type of water soluble black ink there is, they all have the same components. You could state that they have different components, or you can state if it has the same, right? So procedure. How could we write our procedure? All right, so yeah, let's go procedure. Before we do procedure, let's do the easier part first, which is our apparatus and materials. So let's draw. So remember, we need our chromatography paper, right? Put a line on it with a pencil. We put the drop of ink on it. So this is two different inks. So we're going to use two different papers of the same size. and we put the inks, the drop of inks on the paper, and we put both in. So put them in separate beakers that has, let's use alcohol. Right? So both beakers have alcohols. Put the paper inside. Right? So that means our materials that we're going to use would be the chromatography papers. We need beakers. We need alcohols. We need a pencil. We need ruler. And we need droppers. All right, so using that, let's write our procedure. Let's go, step 1. So alcohol, ethanol will do. So just the basic ethanol will do. All right, so step 1, what do you think step 1 will be?
To put the dot on the paper,
Put
or to fill the beaker with ethanol. Or
all right, so your first step would be to, all right, so not say fill because we don't need that amount, that a lot. So let's say put 10 cm cube of ethanol in each beaker. All right, so that's step 1. Step 2. What would we do after that?
oh,
What would we do after that for step 2?
you put the dot on the paper. The ink dot.
All right, so let's fix up that one. So we're going to use a pencil to draw a thin line. Thin line about, let's say, 2 centimeters from the bottom of each paper. Then you can drop. So 1 drop of ink in the center of the line. So we're going to run out of space. All right, so you do 1 drop of ink first. Then after that ink is dried, then you do another drop of the ink. So you say, wait until it is dried. So wait until it's dried, then add another drop.
In the same spot, sir?
In the same step? Yeah, you can. Yes, you can have it in the same step.
What will be the purpose of that?
All right, so the purpose of this is to ensure that you have enough ink present in order for the components to actually spread or be released from it. Because if you use 1 drop sometimes, it's too dilute. So when the colors start to spread, you actually will not see the colors distinctly.
Okay.
Right? So we do 2 drops just to actually get to have that distinct color change difference. The reason why you allow it to dry is because if you put the drops consecutively, it can actually damage the paper. So just imagine you dropping water on a paper. If you don't wait until the first one dries, then because of that wetness, it can cause the paper to actually get damaged. So that's why we allow it to dry first.
Okay.
All right, so we do that, and then we can just have one more step, step 3. What do you think that one would be?
Put the paper inside the alcohol, I don't know. Submerge it. Not really. No, not submerge. That's the wrong word.
What's that?
Just to tip the paper in the ethanol.
Great, so put the papers in each beaker with ethanol, and it's important to state, ensure the ink is not directly touching the ethanol.
Why?
So if the ink touches the ethanol directly, it will cause it sometimes to not allow the colors to actually spread out. So we try to ensure that if it does touch it, it's not covering the entire portion where the ink is. Right? So we kind of actually ensure that the ethanol is slightly on the line that you draw with the pencil or slightly below it. But the main thing is to ensure that the paper itself is inside the ethanol. And also the paper should be straight, that's vertically, so it should be in a vertical position.
Okay, that's some precautions right there.
Right? And then finally, you tell them what to observe, which means so after, let's say, 10 minutes, or you can have 5, you observe the different color on each paper. All right, and then the data to be collected. What important thing would we need to collect if we do this experiment?
The different types of colors that we observed coming
Exactly.
from the ink.
So the different colors on each paper. All right, so repeat step 2. Step 2 is use a pencil to draw a thin line about 2 centimeters from the bottom of each paper. Then drop 1 drop of ink in the center of the line. Wait until it's dry, then drop and then add another drop. So use a pencil to draw a thin line about 2 centimeters from the bottom of each paper. Then add 1 drop of ink to the center of the line. Wait until it's dried, then add another drop. All right, the variable to be controlled. So what variable would we need to control?
The amount of ink you put on the paper.
Exactly, so that's the main one. So it's important, it says just variable. So we look at the main one, which is the amount of ink that we use per paper. All right, and finally discussion of the results as they relate to the hypothesis. You may include a diagram to illustrate your discussion. All right, so remember the hypothesis was that all have the same components. So let's discuss what our observations would be. So if we use a diagram, then we can just draw the two papers. All right, so do you think all black inks have the same amount of components? So because our hypothesis says it does, then that means in on our paper, we will have the same colors. So let's say this is our baseline here, or pencil line. Then we have the same colors being separated. So we have one color here, and let's use two colors, right? So in both cases, both papers will produce two different colors, two of the same colors, and then you state which one will be closer to the ink drop and which one will be further away from the ink drop. So let's go. All right, so which two colors can we use to say that it makes up black? Because I am not good with colors.
Oh, wow.
Which two colors can we use?
Purple and blue.
Purple and blue.
I have to look that up.
I think that would be. Let's use purple and blue. All right, so we're going to say that the bottom one here is purple. So the bottom one is purple, the top one is blue. So your discussion would state first that two colors would be produced on both papers.
It's blue and brown.
Blue and brown. All right, so let's change purple to brown. All right, so two colors will be produced. The blue one, so the blue would be closer to the baseline than the oh, it should be brown. Yeah, it doesn't matter. Than the brown. Why would that be the case? Why would one be closer to the baseline than the next? Anyone knows?
Where's the question? Why would blue be closer to the baseline?
Yes, why would blue and brown be at different height on the paper?
Because one is naturally lighter than the other.
So lighter. All right, so one reason is that one is lighter than the next, but that's not the main reason though. What would be the main reason why they both are not at the same height? All right, so meanwhile you're thinking, let's write that one. So density is 1. And the main one is their solubility.
Solubility.
So how well is the brown color soluble in your ethanol than your blue color? Right? So if it goes higher, that means it's very soluble. If it goes lower, that means it's not that soluble. All right, so both density and solubility works hand in hand. right? But the main reason why they move would be because of solubility. Everyone got that?
Yeah.
All right, so that's all that you would need to jot down right there.
Let's take a do back over the diagram, please.
This one?
Oh, the last one, when you talk about the hypotenuse.
Oh, this one here. So it's just to
Yeah.
it's just to draw the paper. So let's say we draw the paper. I remember we have our pencil line at the bottom here, and you just, all right, so in this case we have two different colors being produced. So you can do two little lines here and you label which one is which. So for both papers, because we said that they have the same components, for both papers they will be at the same height and the same colors will be observed, brown and blue. And then you explain why you would say that they would have the same colors and why each color would be one is below the next, which is based on solubility and density. So if you're lighter, you're going to travel further up. If you're heavier, you're not going to travel a lot up. All right, so before we're going to end for this week, because we're going to continue next week, let's just do one more of this question 3, and then we can finish off for today. Let's look at 2013, question 3. All right, good one. So it's based on the one that I explained just now. So we should be able to do this one quicker. All right, so it says, when aqueous solution of copper 2 sulfate is electrolyzed using copper electrode, the mass of each electrode changes. You are provided with 2 mole per dm cube solution of aqueous copper 2 sulfate. The hypothesis here states the change in the mass of copper cathode for a fixed time period is dependent on the concentration of copper 2 sulfate solution. Plan and design an experiment to investigate the hypothesis. All right, so the question gives us the type of experiment it is, which is electrolysis, right? I just did that at the start, so this should be easier to go through. All right, so remember in our electrolysis, we have a container that has our electrodes. One is positive, one is negative, and then it's connected to a battery supply. And we have our solution or electrolyte. All right, so we have 10 minutes. Let's use that 10 minutes. So the aim of this experiment, so your aim would be taken from what your hypothesis states. So we said that the hypothesis is the change in the mass of the copper electrode is dependent on the concentration of the solution. So the aim, or aims normally start with, so it's very easy because we normally just use these type. So to determine, you can start it with that, or to investigate, or sometimes to find out. All right, so this one, we can start it with to determine. So we're going to determine if the mass of the, so if the mass of the cathode is dependent on the concentration of the solution. So the concentration of copper 2 sulfate, CuSO4. All right, so that's our aim. So we're going to check or determine if the mass of the electrode is dependent on the concentration of the copper 2 sulfate solution. So our apparatus and materials will be everything that we have here. So we just write them in words. All right, so we need a battery, we need wires, we need copper electrodes, we need the copper 2 sulfate solution, we need, what else? It says, yep, that's all we need. So the electrodes, the wires, the battery, and the solution. And it says something about time so that we can add a stopwatch. All right, so procedure. All right, so what's the first thing you think we'll do in our procedure?
Set up the apparatus.
All right, so the easy part is, so just like at this point where there was no space to draw the diagram, you can actually draw the diagram there on the paper to make it easier for you to write your procedure. Because since we have the diagram there, we can say, you can say set of apparatus as shown above. All right, so that's the first one. Next one would be,
Switch on the current.
what's that? All right, so next one is, you're going to tell them to pour a specific amount of copper 2 sulfate in your container. Oh, sorry, apparatus, one thing is missing here, your container to put your electrode, your electrolyte in. So let's use a beaker. So in step 2, you can say pour. The beaker is normally 250 cm cube. It holds the normal size. So let's use 200 cm cube in it. So pour 200 cm cube of copper 2 sulfate in the beaker. All right, then we tell them to connect the battery, and record, not record, should be start. So connect the battery and start the timer and observe. Let's use 10 minutes, no, 20. Observe for 20 minutes. And then last, after 20 minutes, measure the cathode mass using a digital balance. So that means we need to add this back to our method or materials here. So you can add digital balance here. All right, so that's all that you need to do. All right, and as you notice that sometimes when you write your procedure, you sometimes have to go back and edit your apparatus. All right, so always, once you write your method, go back through and ensure that all your method, all your apparatus are listed there in your method.
So a
Yes.
digital balance is same as an electronic balance?
As a?
Is a digital balance same as an electronic balance?
Yes, the electronic balance is the digital one. All right, so you just put it on it and it gives you the reading, so you don't have to do a lot of work. All right, so that's our procedure. 2 variables to be controlled. So this time
for pouring the solutions.
wait, Wait, there's one more thing that we have to do for method, sorry. Because it tells us that we have to change the concentration of the copper to see if the masses change. So therefore, for step 5, you can say repeat for different concentration of copper sulfate. All right, so doing it one time was for one concentration, doing it for the next was to change the concentration. So 2 variables to be controlled. What's the first one?
The concentration of the solution and the time.
All right, so one thing that you said shouldn't be included. So the concentration is not a part, because remember for step 5, we're going to change the concentration and do it again. So the control, all right, means that we're not going to change that aspect of the experiment when we redo something. And we're redoing it with a different concentration, so therefore that will not be controlled in this case. So the other one that you said would be controlled, so the time for experiment is controlled, so the 20 minutes would be the same for the 2 different concentration. All right, what could be another control variable? All right, so the other one is taken from step 2. What would be that?
Or the amount of
The amount that you boil.
Exactly. So the amount of solution used. So even though we change the concentration, we're going to still use 200 centimeter cube. So those are the 2 main control variables for this experiment and your data to be collected. So data to be collected would be that we're measuring the
Mass.
so measure the measurement of the mass of the cathode. So that would be what would be collected. And then we're going to discussion of results, whether the hypothesis would be accepted or rejected. So let's look back at the hypothesis. So the change in the mass for a fixed time is dependent on the concentration. All right, so let's go. So first, we can say that the hypothesis should be accepted, because if you change the concentration of your solution, then the mass of your cathode will also change with it. So first thing is that it's accepted. Why would you think that's the case? So that would be the discussion part. Why would, if you increase the concentration, the mass of your cathode will also change with it. If you decrease it, it will change in that regard. So your cathode, just for a purpose, your cathode will get bigger, all right? So if your concentration is high, it's going to be very big. If it's low, then it's going to be big, but not as big as if it's concentrated. Why do you think that would be the case?
So
Our
what's the
question,
question?
why would the concentration affect the mass of your cathode? Because remember, your cathode is your, which one is it? Your negative electrode, right? But your cathode is made up of copper. So copper makes up this cathode. And in your solution, the ion that will be attracted to it would be your copper 2+ ions. Right? So when this is attracted to this electrode, it's going to actually gain electrons. So it's going to gain 2 electrons to become your copper metal. So this copper metal will form a layer on this electrode, so it makes it get bigger. All right, so this layer that is formed would be made up of copper. So it makes this entire thing bigger in mass. All right. Now, if the concentration is low, this layer is smaller. If the concentration is high, then the layer gets bigger. What link does concentration has in terms of getting the layer big and small?
Okay.
When there's a high concentration, there's more copper ions or something like that.
Yeah, you're on the right track. So there is more copper ions. All right, so if the concentration is more, there's more copper ions. So if there's more copper ions, then more copper metal will be produced. And the vice versa will happen if it's of low concentration. So if it's low concentration, you have less copper ions present, so you get less copper metal being produced.
More copper.
Right, so that is the reason why concentration will affect the mass. Any question on that?
No, I
No.
understand.
All right, so
Yeah,
finally,
okay.
one possible source of error that will be experienced. What error would we experience if we try to do this experiment?
I would say the amount of time they will leave before it could be less.
The amount of time?
Yeah, you go for the time limit.
All right, so.
Or less than time limit.
Okay, so the timing of the experiment can differ when changing concentration. Right? Or you could say that the volume, the 200 cm cube, it can be slightly different based on an error that is known as paradox error. Anyone knows what that is?
That is when you're measuring something and you had to go down eye level. And if you measure, like if you go like watch it in the wrong direction, then your calculation.
Exactly. So your paradox error is if you're not viewing your measuring instrument at eye level. So if you're standing and looking down at it, or you're looking up at it, then that's paradox error. Right? So, and we all would be guilty of doing that. Right? We never want to stoop, especially when it comes to stooping. We never want to stoop to go down to eye level to read it. We normally just stand and read, which can actually change or alter the exact volume of what we should be using. All right, so any of those errors would be accepted. All right, guys, so before I
Still
close, go again.
I'm still wondering if you could tell us what would be two manipulated variables to this.
All right, not hearing you so clearly. All right, just type the question there so I can see. So meanwhile, typing is, anyone else has a question before we finish off?
No.
Oh, the manipulating variables. All right, so the manipulating variables for this would be, it's just one. So it's never, in every experiment, it's never more than one manipulating variable. And the manipulating variable would be your concentration of your copper sulfate solution. All right, so that's the only thing that we're going to change if we're doing this experiment. So that's what the manipulating variable is. And for purpose, your responding variable would be your mass of your electrode. So that would be the responding.
Answer?
What's that?
What's the definition of a manipulated variable? That's what it's called?
All right, so the definition of manipulating variable is that this is the quantity that you change when you're repeating an experiment. All right, so it's the quantity you change when you're repeating the experiment. So if you remember here, we said that first we use a specific concentration, and then step 5 says we're repeating it for a different concentration. So because we change the concentration again and we're doing the experiment, then that means that is the manipulating. The responding would be what you are observing when you carry out the experiment. And that would be taken from step 4, which we say that we're measuring the mass of the cathode. And then we already know the control is when we're repeating it, what exactly we keep constant from the first one to the second one. That's clear?
Yeah.
All right. Any more questions? All right, so no more questions.
No, I'm good.
All right, so as I told some persons before, I will continue this session next week, same time. All right, so we can finish off with these questions. All right, so see you guys next week, same time, with the same ID and password as this week.
Okay, sir. Thank you.
All right, no problem. All right, so see you guys.